Welcome to the deep dive. For decades, space travel felt like something reserved solely for, well, superheroes, superpowers, and frankly, astronomical budgets. Space was the exclusive domain of major world governments. But suddenly, in the span of less than a decade, it's becoming routine, affordable, and almost boring.
Almost, yeah. And that shift turning arguably the most complicated engineering feat in human history into something bordering on routine, that's really down to one massive technological leap: mastering reusable rocket technology.
Exactly. We dove deep into a whole stack of sources detailing this transformation, really looking at how the economics of aerospace were completely rewritten, largely by SpaceX.
Right.
So our mission today, for you listening, is to uncover how building a rocket that can actually land and fly again, that core concept, has fundamentally reshaped our place in the universe. And maybe more importantly, why this tech is absolutely essential if we want the future of space to be, well, open to everyone.
It truly is the single biggest factor. It's changed the entire economic equation for sustainable space exploration.
Okay, so let's unpack this. Let's start with the core problem. The staggering economics of expendable rockets. For most of space history, rockets were just single-use vehicles, by definition.
Disposable.
And our sources gave us this killer analogy for that model. Really makes it clear.
Oh, yeah, the 747 one. It's perfect because it makes the commercial absurdity just immediately obvious.
Right. Traditional rocketry is like building the world's most advanced 747, flying it across the Pacific once.
And then just ditching the entire plane into the ocean. Gone.
And the most expensive part of that plane, the engines, the main structure, completely lost every single time.
Exactly. And this is why space travel was just historically so expensive for NASA, for everyone. You had to build a brand new, incredibly complex rocket for each mission.
And that component you were throwing away, the first stage booster, often accounted for a mind-bending 60 to 70% of the rocket's total cost.
Think about that, 60–70%. You're not just paying for fuel and the launch operations, you are eating the cost of hyper-complex manufacturing, materials, science, everything, every single time you launch.
Wow.
And that doesn't even touch the high insurance costs, the safety margins you need for launching brand new hardware that's inherently, risky.
So let's put some numbers on that for you, just for context. We were talking figures that basically barred most of the world from even thinking about orbit. A single space shuttle mission.
Yeah.
Cost somewhere between $450 million and $1.5 billion per flight.
Unbelievable numbers.
And even a simpler mission, say launching a communication satellite with a traditional expendable rocket, like an Atlas V or an Ariane 5 back then, you were reliably looking at $150 million to $300 million. Easily.
That price point just locks it down. Space becomes the exclusive playground of a handful of super-rich government agencies.
Precisely.
Yeah.
Which is why the arrival of the reusable rocket wasn't just some technical tweak. It was like a commercial earthquake. It completely shattered a half-century-old business model.
Absolutely shattered it.
So if that's the problem, these hundreds of millions in launch costs, the billion-dollar question is, how did they actually crack it? How did they solve the physics and the economics?
Okay, so that's where the SpaceX revolution really kicks in. Elon Musk founded SpaceX back in 2002, and he had this incredibly ambitious, almost laser-focused mission from day one. Make space travel affordable, make it sustainable, with the ultimate goal of getting humanity to Mars.
Right. Mars was always the big picture.
Always. And their proof of concept, the vehicle that fundamentally changed the whole conversation, was the Falcon 9 rocket, and later the Falcon Heavy, specifically that reusable first stage.
It's easy to forget now how, well, impossible this seemed just a short while ago. I remember watching those early landing attempts, the explosions, the failures.
Oh, yeah, the blooper reels were long at the start.
It looked like pure science fiction. The engineering complexity required to slow down this massive, like 20-story booster falling from space, steer it through the atmosphere, and then land it vertically, gently, on a tiny platform. It's just phenomenal.
And that phenomenal engineering, it's really encapsulated in the mechanics of how reusability works. It's a multi-step dance.
Okay, walk us through it.
So first, obviously, you have the launch and stage separation, standard stuff. But then the booster performs this critical return maneuver. It's not just falling passively.
It's flying back.
Exactly.
Yeah.
It uses engine burns to flip around, point the engines forward, and slow itself down. It uses little cold gas thrusters for fine attitude control. And crucially, it deploys those 4 big X-shaped grid fins.
Ah, yes, the grid fins. Those waffle iron-looking things.
They look strange, but they're essential. They provide aerodynamic control, basically steering the booster back through the atmosphere. They act like huge air brakes as it descends.
And then the landing itself.
It's fully automated.
Aiming for either a concrete landing pad back near the launch site or
for missions needing more performance, aiming for one of those autonomous drone ships positioned hundreds of miles out at sea, which is another incredible feat of engineering in itself.
landing on a moving platform in the ocean. Wild.
And once it lands, the clock starts ticking immediately for the turnaround. The sources really emphasize that rapid inspection and refurbishment, sometimes done in just a few weeks, is absolutely key to making the whole economic model work. It can't take months.
Right, the speed is critical.
And the pace of innovation here was just breathtaking, really. You can actually trace the velocity of their progress through some key milestones. Think about this timeline. The first successful landing of a Falcon 9 booster on land, that was December 2015.
Okay, so not that long ago.
Not at all. Then, just a few months later, April 2016, they nailed the first landing on a drone ship at sea. Much harder. Then came the really crucial step, March 2017, the first reflight of previously flown booster. That proved it wasn't just a stunt.
That proved the concept.
Yeah.
That it could actually be reused reliably.
Exactly. And then the ultimate stamp of approval, maybe. May 2020, they launched their first crewed mission, Demo 2 with Crew Dragon, using a booster that had flown before.
Wow, okay, hold on. Using a reused booster for a crewed mission, wasn't that seen as a massive risk? I mean, the traditional space sector, NASA included, was built on this idea that brand new hardware is always safer, especially for astronauts. How did the sources address that safety concern?
That's a really critical question, and yeah, there was definitely skepticism. The sources stressed that the safety case relies on a few things. One, incredibly rigorous inspection and refurbishment processes. They check everything.
Okay.
But maybe counterintuitively, the safety case also relies on the sheer volume of flight data they were gathering. Because they were launching and landing boosters so frequently, sometimes multiple times a month.
Right, way more than older programs.
Exactly. They were identifying potential failure points, understanding the hardware's behavior, and iterating on design and processes far faster than older programs that might launch only once or twice a year. The data itself demonstrates reliability over many flights.
So it's reliability through iteration and proven flight heritage, almost like how airlines operate. Constant use reveals weaknesses faster.
Precisely. Meticulous testing ensures components that see the most stress are either verified as safe or replaced. It's a different philosophy, built on data and rapid cycles.
That makes sense. Okay, so now we know how it works, and that it works even for people. Let's get to the bottom line. The cost cascade. This is the big so what, the financial impact for everyone wanting to get stuff into orbit.
Right. Reusability just fundamentally attacks the 2 biggest cost centers, manufacturing and launch frequency. By essentially eliminating the need to constantly build the most expensive part of the rocket, that first stage, your fixed costs just plummet.
You're shifting from buying a new asset every single flight
to basically maintaining and refueling an existing one, like an airplane.
And the numbers, when you compare them to that traditional $150 to $300 million price tag we talked about earlier, are just staggering.
Oh, absolutely. Even when SpaceX flies a brand new Falcon 9 booster today, which is rarer now, the list price is already down to around $62 million, a huge drop. But crucially, when they utilize those flight-proven, reused boosters, which is now the standard way they operate, the launch price drops even further. We're talking somewhere between $30 and $40 million per launch.
Okay, just pause there for a second. You listening, think about that magnitude. We're talking about reducing the cost of accessing space by, what, 75%? Maybe even 80 or 90% compared to the old model?
That's that level of change, yes.
This isn't some incremental improvement. This is like the cost of computing dropping through the floor in the 80s. It totally changes who can even consider being a customer for space launch.
And that cost reduction ripples outwards. You don't just save on manufacturing. That faster turnaround time we mentioned, it allows them to dramatically increase their launch frequency. SpaceX now launches dozens, maybe over 100 times a year across its fleet.
Which increases the supply of launch services. services.
And further lowers the effective cost per flight because of economies of scale. More flights mean the fixed costs of launch pads, recovery teams, etc. get spread thinner.
And what's really crucial here, as noted in the sources, is that SpaceX's success hasn't happened in a vacuum. Their dominance has fundamentally shaken up the entire market.
Oh, definitely.
Competitors across the globe,
Yeah.
Jeff Bezos' Blue Origin Rocket Lab, even the big government-backed players like Europe's Arianespace, they're all scrambling now. They have to develop and invest heavily in their own reusable systems just to stay relevant.
Reusability isn't a novelty anymore. It's basically table stakes now. If you're developing a new large rocket and it's not reusable, you're likely already commercially non-competitive on price.
But it's not just about the price tag, is it? Let's touch on some of the non-monetary advantages of this model, because the benefits go beyond just dollars and cents.
That's a great point. For one, there's the environmental aspect, which often gets overlooked. Reusability dramatically reduces waste. Think about it. Fewer giant rocket stages being dumped into the ocean or burning up on re-entry.
Yeah, less debris.
Less debris, and critically, fewer massive industrial emissions associated with constantly manufacturing these exotic, expensive, multi-story machines from scratch. Building rockets is energy intensive.
Okay, that makes sense. But the benefit I find maybe the most compelling, and it ties back to your point on safety through iteration, is the sheer speed of innovation it enables.
Absolutely. When you have a reusable system, your engineers get data back constantly. They can test improvements, tweak designs, and see how they perform on real-world flights in rapid succession.
You're not waiting months or years for the next data point from a single-use rocket launch.
Yeah.
You might get data back weekly.
Exactly. That ability to learn and iterate quickly just accelerates the entire development cycle for everything. Better engines, lighter structures, more efficient flight profiles, it feeds on itself.
And if we connect that to the bigger picture,
Mm.
what does it mean for global accessibility? You touched on it earlier.
Well, it means space missions, putting satellites up, doing research. It's now genuinely within reach for countries, for companies, even universities that previously couldn't even dream of affording it. This cost reduction is the democratization of access to orbit, literally.
Of course, success hasn't made it easy. It's tempting to just focus on those incredible smooth landings we see now, but we shouldn't gloss over the immense technical difficulty that still remains.
No, absolutely not. Even with all the practice and data, landing a 20-story metal tube vertically on target using rocket engines, it still requires extraordinary precision. Things can still go wrong.
And that precision comes with a maintenance burden, right?
Uh-huh.
These rockets endure immense stress vibration, heat during re-entry.
They require meticulous inspection, refurbishment, and maintenance to ensure they stay flight-worthy. The goal is efficient maintenance, like an airline, not rebuilding. But there's always a risk that wear and tear demands more extensive, expensive repairs.
And we shouldn't forget the upfront cost. Designing this, building the landing pads, the drone ships, the refurbishment facilities, that required a huge initial investment in R&D and infrastructure.
Billions. Something only massive private funding, like Musk provided, could really sustain through the early failures.
Indeed. But SpaceX isn't stopping with Falcon 9 and Falcon Heavy. And that brings us to the next, almost unbelievable chapter in this story, Starship.
Ah, Starship. Yeah, that represents the absolute next level of ambition. It's designed from the ground up to be a fully reusable spacecraft. Not just the booster, but the upper stage, too. The part that actually goes into orbit or beyond.
Fully reusable, the whole thing.
The whole stack. The idea is that Starship will eventually replace all other SpaceX rockets, Falcon 9, Falcon Heavy, even the Dragon capsules. It's meant to be their single, unified vehicle for everything. Earth orbit, lunar missions, deep space travel.
And the vision for it is just audacious. Starship is designed to carry over 100 tons to orbit in its reusable configuration.
That's mammoth capacity, far beyond anything currently flying regularly.
And the target launch cost, which is the really mind-blowing part, based on achieving that full reusability and a very high flight rate, they're aiming for under $10 million per flight.
That figure, if they achieve it. That's where the entire dynamic shifts again. dramatically.
Mm.
If you can launch 100 tons for $10 million, space launch stops being a barrier and starts becoming almost a marginal cost for many potential industries and applications.
Okay, but under $10 million, that sounds almost impossibly low, maybe even reckless given the complexity.
Yeah.
Is there skepticism in the sources or in the broader industry about hitting that price point? It requires so much to go right.
Oh, there's definitely healthy skepticism, absolutely. Hitting that price point requires an unprecedented level of refurbishment efficiency, turning the vehicle around potentially in days, not weeks. And it requires a flight rate that hasn't been seen before, maybe launching the same vehicle hundreds of times, perhaps dozens of launches per month across the fleet.
A true airline model for space.
Exactly. But the logic holds. If they achieve near-total reusability, where the only major cost per flight is fuel and ground operations, then that $10 million number isn't physically impossible. The massive fixed cost of the vehicle gets amortized over potentially hundreds or thousands of flights instead of just one.
And that potential efficiency connects directly to the really big picture goals. Right?
Absolutely. Starship is the key to affordable lunar landings. It's already been selected by NASA as the lander for the Artemis program to put humans back on the moon. It's absolutely central to the whole vision of Mars colonization, making trips affordable enough for large numbers of people and cargo. And it even opens up possibilities for rapid point-to-point travel right here on Earth.
Using it like a suborbital airliner.
Potentially, yeah. Turning long-haul flights into maybe 30-minute hops by briefly leaving and re-entering the atmosphere. It's the ultimate scaled-up expression of that initial SpaceX mission, making humanity multiplanetary and maybe shrinking our own planet, too.
So when we step back and look at this whole incredible trajectory, reusable rockets have clearly done far more than just save one company some money. They have, pretty definitively, democratized access to space.
No question.
Turning what was an exclusive, incredibly expensive government privilege into something closer to a sustainable, affordable service. Something potentially available to startups, universities, developing nations across the globe.
It proves that reusability isn't just possible. It's absolutely essential if we want to unlock the next era of space exploration and development.
The initial vision, the engineering boldness, and frankly, the tolerance for early failures have compressed what might have been decades of traditional slow aerospace evolution into just a few short revolutionary years.
The pace has been truly remarkable.
Okay, so here's a final provocative thought for you to mull over as we wrap up. If the cost of launching 1 pound or 1 kilogram of material into orbit truly approaches the cost of standard commercial freight like sending a shipping container overseas, what happens next? How rapidly does space infrastructure development, things like orbital manufacturing, maybe space hotels, permanent lunar bases, how quickly does all that accelerate in the next decade or two?
That's the question, isn't it? It stops being about if we can build things in space and starts being about when and how fast. The economic barriers that have held us back for 60 years are falling much faster than almost anyone predicted, which means the timeline for building a real, sustained human presence off Earth, well, it might be shrinking dramatically right before our eyes.